Corinne Roberts presents her Capstone Project for her STEM diploma with her mentor, George Iwaszek. Congratulations, Corinne, on your upcoming graduation with the BHS Stem class of 2025.
Science program, so people like us can get involved in some really heavy duty cool kind of stuff to contribute. You can't do that in nuclear physics. I mean, I don't know anybody who's ever operated a sniper on this playing a lot of people with telescopes, so you can contribute stuff. And so what we're going to talk about here, Corinne's going to start off by talking about exoplanets. She'll explain what that is. She's going to set the big picture. And then I want to talk more about what I do with my observatory and the kind of things that I do. So again, we're going to try to keep it light, fun. By the way, as we go through it, if we say something that doesn't make sense or you have a question, go ahead and stop us asking. Okay? Let me quick start with this. Who's a professional astronomer? Great. That means we can give you all kinds of yes. Okay, go for it. You all set?
Yeah. Hopefully, is this better?
Yes. No.
Perfect. Okay, so we are going to go over exoplanet transits through light photometry. My name is Corinne Roberts, and my mentor was George Iwaszek. So let's start with NASA. Most of us, I'm assuming, are familiar with it. It was created by Congress in 1958, and it is the front of the US's focus of space race and the space exploration. So it's always been focused on one question, which was, is there life in other universes, in other solar systems, other Earths, stuff like that? To figure this out, we've launched four space missions. Transiting Exoplanet Survey Satellite, which was acronym is TESS. Its primary goal is to find exoplanets that orbit bright stars. It was launched in 2018. The Kepler Space Telescope was launched in 2009, and its goal is to find just any planet, just any other solar systems. The Hubble Space Telescope, which I'm sure some of us have heard of, was launched in April of 1990. And while its primary directive is not finding exoplanets, it's provided a lot of data that is very, very useful for exoplanet finding. And then most recently, we have the James Webb Telescope, which was launched in 2021, and it is it's the best telescope we have so far. It's revolutionized how NASA finds exoplanets and how we can see them. There's also been 42 different ground-based missions. I can't name them all because that's a lot. But basically, space is very good for focusing without the atmosphere distortions. It helps us be able to see farther and with more clarity. But the problem with space is that you can't look directly at super, super bright stars because you'll blind the camera because there's too much clarity. So to solve that, we use Earth-based telescopes that allow us to see at brighter stars and with more, not consistency, but they're a lot cheaper to use just a telescope like this than to send one up into space. So what exactly, we keep talking about exoplanets. What exactly is an exoplanet? They are planets that exist outside of our solar system. So in order to qualify, they have to be spherical, and they have to orbit around a sun, and they have to remove neighboring neighboring debris from its orbit. Basically, this means as long as you have a sphere-ish, it could be football, could be an actual sphere, anything like that, and it has enough mass to move the objects that are in front of it to either orbit around it like a moon or to fling it from its orbit, then that qualifies. So there are 4 known categories of exoplanets. They're based on their size, proximity, and composition. So gas giants are also known as hot Jupiters. There's ice giants, which we call Neptunians, and then there's super Earths and terrestrials. So these are the solar system distances. Up close, here, we have hot Jupiters, which are the closest to their sun, and they're called hot because they superheat because of how close their orbits are. They're like inside their star almost. They like superheat to like thousands of degrees. Next, we have terrestrials and super-Earths, which are inside what astronomers call the Goldilocks zone. Which is where we can assume that life could happen. So it's not too close to the star, and then it's not too hot, hence Goldilocks. They're middle-sized planets, and they're mostly made of like rock. And Neptunians over here are in the far outer reaches of our solar system. Their orbits are 84 Earth years to go around once. They have, they're so far from their sun that they're super cold, and so they're constantly just frozen and all of this. So for orbits, hot Jupiters have smallest. They can be a few hours, couple days. Terrestrials or super-Earths and super-Earths can go from anywhere from a few weeks to like a couple years. And then Neptunians are the ones with ridiculous orbit lengths that would take an entire human lifetime to go around once. Oh, yeah. Yeah, go for it.
Hot Jupiters absorb sun's heat, so like the star's radiation.
They get blasted with radiation and they don't absorb it very well. They kind of just disintegrate.
Actually, I'm going to talk about a hot Jupiter, what's happening to one of these hot Jupiters. All the observations I've done on hot Jupiters, we're going to talk about one in particular that's so close to the star, it's being ripped apart. Yeah, but there are some that are stable. But yeah, that's a beautiful question. No, you don't want to be there. You don't want to be in any of those hot Jupiters. Trust me.
Okay, so super-Earths are typically larger than Earth. They can be made up of rock or gas, and they are most likely to have life. This is because they're in that Goldilocks zone. They can also have stuff like carbon or water, stuff like that in their atmospheres so that we can look at life, hopefully. Neptunians, again, are the ice planets. They're so far from their sun that any water that they do have freezes. They have like a solid core and then gas that's been frozen surrounding it. They're super far from their sun, and they're also pretty big. They are also we think that they're going to be the most common type of exoplanet, but because they're so far from their star that they're really hard to see with how we have viewed exoplanets. So hot Jupiters are absolutely massive. They're so close to their stars that they are superheated to thousands of degrees. They're planets of gas and dust, and they have a solid core. And yeah, they're really hot. Terrestrials are smaller than Earth to Earth-sized. They're a habitable zone. They're inside the Goldilocks zone, and they're covered in rock, and they can be rock or water. So we have 4 main ways of finding these exoplanets. These are the 2 that have been successful, but they're the least common. So gravitational lensing uses, let's do some background. So think of a bowling ball on a trampoline. When it goes, it creates like a divot. This is the same thing that happens with objects of great mass when they interact with the fabric of space-time. They create this dip, which we can see right here. Using this, we basically create a natural lens using the gravitational waves that look like this, and through it we can sometimes, it's like a microscope. We can see, or it's a telescope. It's nature's telescope, and we see from where we stand, we can see a planet, and then we can use that planet's gravitational lens to see the one beyond it. So this is direct imaging. It's the newest method of finding exoplanets. It's only possible with the James Webb telescope, and James Webb sees in infrared. So this is what, using the infrared, we can see the heat of the star and the heat of the planets. And by blocking out the star, we can see all these little planets. It hasn't been used a whole lot because it's relatively new and it's also hard to see. The only planets that you can see with this are hot Jupiters. So, radial velocity. As a planet orbits around a star, the gravity of the planet tugs a little bit on the star. So this causes the orbit to kind of spiral a little bit. And because we can see these like changes in how far the star is going, we're able to see like if it's traveling away from us or if it's coming back towards us. And this can allow, and because it's red light, if it's traveling away and blue light is approaching, what's that law called?
What's that? Oh, Doppler shift.
Yeah, the Doppler shift law. It's basically a minor but consistent wobble in gravitational pull that allows the astronomers to see the mass of the planet. This is the transit method. This is what my mentor and I used this summer. It's very similar to a solar eclipse. So as the planet goes in front of the star, we can see the corresponding dip in light as the planet blocks some of that light from us seeing it. The bigger the planet is, the more light is blocked, or the bigger and the more close to the star it is, the more light is blocked, and the same is true in the opposite. So the farther away from the star the planet is, the less light we see, and okay, that was really bad, sorry. Basically, as it goes around the face of the star, it blocks light, and the bigger the planet, or the closer it is to the star, the more light is blocked. And then the farther away it is, it's harder to see. That's why Neptunians are harder to see than hot Jupiters. So, exoplanets are really hard to find. We have only known about them for about 25, 30 years. In that span, we have found 5,800 exoplanets. 90% of them have been found by TESS and James Webb. So this is what we can learn from the light curves that we get from the transits. We can see how long the planet orbit is. We can have the planet size and the shape of the planet, stuff like that.
What are light curves?
So light curves are what we track from as the planet goes in front of the star, we get this little curve right here. And right here, we're literally looking at the amount of light is coming off of the star. And because of that, we can tell where the light dips and where it comes back up.
Like this.
That's because the planet is going in front of the star. So it's blocking a little bit.
I'll talk more about this too. So, this is a good question.
So does that make sense?
Yeah.
Oh, yeah.
So functionally, you're just measuring an eclipse of the star.
Yeah.
By the planet from our perspective.
Yeah. It's exactly like a solar eclipse would be here, except we're a lot farther away. So this is what a light curve would look like. This is information from TESS. We can't do light curves to this extent because we have atmosphere and daytime and stuff like that. So this is a full orbital period. This is a light curve for WASP 1b, which is an exoplanet that is a hot Jupiter. And we can see here that because the exoplanet curve is so deep that it's a large planet and that its it took a while for, actually no, for this one it didn't take a long time because this is the whole orbit. So this is the whole planet going around the star. This is what it would look like, or hypothetically, this is an artistic interpretation of WASP-1b. We can see the gas in the outer layers. I'm sure my chemistry teacher could probably tell you what the colors of the gases are. But, so this is the light curve for TOI 1680b. This is a super Earth, and you can see compared to the last light curve, this one is a lot shallower, and that's indication of a small planet with a long orbital period. Because remember how long, compare this length of time to this length of time. It took a lot longer for the planet to go around, which means that its orbit is wider. Yeah.
Does it matter, like, for those? Okay, so does it matter? Does like it cause any difference if the light difference light curve is like steeper rather than this for light to like happen?
No.
So for light to happen, does it have to be like pretty subtle?
Yes. Normally, yes, because we haven't actually found anything with life, so this is all this is all me guessing. But
your question is not. Oh,
yeah.
but yeah, this is another question that.
It just the longer the curve takes to happen, the farther from the sun the planet is. So that can be good and that can be bad.
So like if it's farther, it would cause lower like temperature.
Yeah.
That's why she calls it Goldilocks. It has to be just right.
Yeah.
It has to be the just right distance away from the parent star.
So this is what.
You got a question?
Oh, sorry.
I'm just curious. I don't know if you'll be able to answer this. Let's say it's orbiting a variable star. How would you take that into account on your light curve?
I'll talk about that too. Wait, go ahead.
I don't know. I'm not gonna lie. He does. I don't.
I'll repeat that question when we get to it. That's actually a really big deal. Sorry, I know I'm not supposed to talk away from the microphone, but I'm doing it because it's easier to do. Yeah.
But yeah, this is an artistic interpretation of TOI 1680b, and so it's a potentially rocky world, and it's a little bit larger than Earth, and it's 121 light years away, which means it would take a long time to get there. So this is the light curve for Epic. That number. This is a terrestrial. So we can tell that this is a very small planet because we can barely see any dip in the light at all. These are the smallest planets, and they're very difficult to find because there has to be a lot of the correct timing and the amount of clarity needed for telescopes to see this tiny little dip is a lot. So this is what it could look like. It's only 6 light years away from Earth, which is pretty good. So this is a light curve for AU microscopy C. This is a Neptunian. So these are, again, the planets that are very far away from the sun and take a long time to orbit. We can see this because of how steep this light curve is, and how long it takes to go across. And this is what it could look like.
Hold on to this for me for a moment. Okay, there you go.
Tell me to do the clicker.
First time I've ever done this.
Mine didn't work.
Oh, I see. that goes, that's good. This thing clips on. Did I get it this time? Did I get it?
It's good enough.
Okay, good. Here, I'll take the clicker. So I'm going to get to your really good questions in a minute. Okay, is this good here? Okay. Hey, so one of the things I just want to put, you asked a really good question. What is a light curve? So she's talked about it. I'm going to talk more about light curves. But here's something I want you to keep in mind. These light curves that we're showing you, these little dips, they are so small. I mean, these planets, these are faraway planets, right? I mean, hundreds of light years away. Light, what's a light year? Does anybody know what a light year is?
5.8 trillion miles.
How many miles?
5.8 trillion miles.
Trillion miles, but what is a light year?
A light year is basically the time of how long it's gonna like take.
How long a photon of light will take to travel in 1 year? 5 trillion miles.
Oh,
So
wow.
these planets that are 400 light years away.
George.
Yeah.
You dropped your microphone.
Oh. My foot wasn't talking? All right, let me try this again. All right. That's not going to work. Here, could you clip it onto this thing for me? I think it will stay there. Sorry. Okay, there you go. Yeah, so these planets are 400, 600. One I'm going to show you is 1,200 light years away, right? 1,200 years for that light photon to go from that star to us. That's a long way away. So when we're looking at these little tiny planets that are 1,000 light years away, there's not a whole lot of light difference. And I'll talk about that, but I was looking for I saw the baseball in there. I saw an analogy. We're looking at changes in light. Like if you held a baseball up and you shined a flashlight on it from 2 miles away. All right, so think about that. I've got a baseball, I've got a regular flashlight 2 miles away, and I shine a flashlight on it. And she comes out with another flashlight that's just a little less bright. That's the differences we're looking at. We're looking at tiny, tiny differences. They didn't discover exoplanets until 30 years ago because they're really difficult to find. Really, really difficult. But as it turns out, with this transit method, even a little schmuck like me can do it. So, because if you've got the right equipment and you know where to look at the right time, you can see it. But we're looking at really, really faint changes. There's no way that you've all looked up at the sky, right? You looked at a star and you mentioned variable stars. There are certain variable stars that you can detect the change in light with your eye. These you'd never be able to do. They're so far away that first of all, you don't even see the star itself with your naked eye. You need special equipment. You need a telescope. And then the change in light is so small that, again, you need special equipment and special software. A lot of what we're doing here now, scientists were just starting to do, host star. I'm going to use this guy right here. There's our host star. So what do we mean by host star? That's the star that is the parent of the planet we're going to look at, right? So this star has a planet around it. I'm not showing you that planet, but this star has a planet around it. So it's emitting light, right? And we know how stars emit light, right? They're basically thermonuclear devices, right? They take hydrogen or helium or something like that, and they smash it together in fusion, and they create energy, right? That's what a star does. So it's creating light, and every once in a while, as somebody pointed out, it's like an eclipse, right? Or this planet, this little tiny planet, moves in front of a star. Maybe it's a big planet, but relative to the star, stars are big things, right? I mean, I don't remember what the relative Earth to our sun is. Our sun is a small star. Do you know what it is offhand? I think it's like 100,000 times, diameter-wise. They're tiny. Planets are tiny relative to their star. But, and this is where I'm going to try to keep it at a good level for this audience. But we have this thing creating light energy, and then it has to travel through the atmosphere of the star. That's called darkening. And then it's going to travel these hundreds, 1,000 light years across interstellar space. What do we have in interstellar space? Dust. Not a lot, but there's enough that over
25 trillion miles, you can really dim some photons. Then it hits the Earth's atmosphere, and as Corinne said, it's murky, it's mucky, right? That's why we put telescopes up in outer space, because we want to get above this muckiness. Then there's the sky background. Where I live, I used to be able to look down south, and Longmont was kind of just a little blip on the horizon. After 10 years, the so-called light dome from Longmont, you all have seen it. You know, it's pretty bright. That's the sky background we're fighting with. So our little photon from 1,000 light years away has to fight its way across space, through the Earth's atmosphere, fight with Longmont, the light from Longmont, until it finally gets to my little telescope. And even then, it's still a problem because, you know, the sun heats the ground up in the daytime. We've all seen those shimmering waves that come off the ground, right? All that is turbulence. All of that makes this imaging kind of murky and mucky. What was the word you used? You had a nice word for it. But anyways, it really messes with the image, right? So that's what's going on. Okay, so I'm not going to talk about limb darkening, but for the scientists or people who are really interested in science, the first thing that happens from, so we got a star, right? This big thing is, it's a star. It doesn't look like a uniform brightness all across, because turns out this star, which is a big ball of gas, has an atmosphere. And as a photon comes out from the nuclear energy zone and goes through the atmosphere of the star itself, it has, well, you know, it has a scattering effect. You all have seen this, right? How many people have seen the moon on the horizon? What color is it? Orange. Why is it orange, do you know?
Really scattering.
It's scattering, the blue light is scattered more than the red light. And so the blue light is scattered away, and what you see is the remaining red light. Same thing happens in the star. And it happens, and because you're looking at a thicker atmosphere here versus in the middle, you have this limb darkening. But I'm not going to talk about it any more than that. It's the reason why it's an important thing is because when I start talking about these light curves in the models, this thing is going to come into play. But I'm not going to talk any more about it. So, unless you have questions. Okay, so what is the transit method? So she talked about the transit method. What are we doing? Well, first of all, back to your question, we have comparison stars. So we're looking at a star with a planet around it that's eclipsing the planet, and we're comparing it to something. We want to compare it to a star or stars that have stable light, right? So that we can do what's called differential photometry. Big phrase for meaning we just want to see the differences, right? And if our comparison star has dips in it, it's going to confuse our ability to tell that really tiny dip from when the planet goes across the face of the star. That's the key, right? That we want to be able to detect that tiny dip, and we need a really stable source. So we want to eliminate variable stars. And actually, as it turns out, the software that we use does that for us automatically. In the old days, you would have to do it by your eye. You have to look at the data and, oh, I'm going to eliminate that. But the software that we use helps us to do that. I'm not going to talk about aperture photometry because that's actually going a little deeper than we need to. But for those of you who are interested, I'll be happy to talk about it. Basically, what we're doing when we look at these stars, and I'll show you an image of what kind of images we collect. But what we're doing basically is we're taking a picture of a star. So those are pictures of stars there, right? But they're pictures of galaxies and such. When I show you my picture, you usually see a bunch of little white dots. That's what we're looking at, because that's all these stars that we're looking at are. There's little white dots in the black sky. We're looking at those in a special sort of way so that we can, again, measure this tiny little difference. So this aperture photometry is just talking about how we set up how we look at these little tiny dots. That's not a very good scientific, that's why I asked if there are any professional astronomers, because they would shoot me if I explained it that way. And I'm not trying to denigrate anybody here. I'm just saying that it gets complicated pretty quickly, right? But ultimately, it's what we're looking for is differences, right? So his question about variable stars, it's very important that we have our comparison stars that aren't variable. That's the key thing. And then you asked the question, what is a light curve? A light curve is, we take a typical transit. You know, she showed a variety of different ones, right? But a typical hot Jupiter transit could be anywhere from 1 hour in duration to 3 or 4 hours. Oftentimes, we're taking a picture every minute. So 3 hours, we got 180 photos, plus we need some baseline. So we probably could have up to 300 photos of a certain region of the sky. Each one of those photos becomes a data point because we're doing some measurement to find that little dip, right? I'll show you some pictures and I'll explain a little better.
Real world example.
What's that?
We can give a real world example
Go ahead.
of a light curve. All you have to do is.
Well, there you go. Yeah.
It's that time period.
Yeah, that.
How long did I turn the lights down?
Yeah, that. Yeah, right. Yeah. Right. Oh, yeah. Go ahead.
So, where do you find a light year? Like using like those telescopes or like
How do I say that question again?
find a light, not a light year,
How do you find it?
light curve?
Oh, well, okay. So she said, how do I find the light curve? I think what you want to ask is, how do we find the star that creates the light curve?
Yeah.
Yeah. So she talked about the various missions that NASA has set up and others have sent up. These missions, specifically, like TESS, for example, Transiting Exoplanet Survey Satellite, it is a couple hundred miles above the Earth, and it's just floating there, and it looks at a certain section of the sky over a period of time, and it just looks there for hours or days at a time. And what it looks for is little blips in changing light.
So like what he did like with the lights.
Kind of, but what they're doing is they're taking pictures, and they're basically, each picture might have 1,000 stars, let's say, and they're looking for changes in light in any of those 1,000 stars. And then we come in, they'll say to us, hey, we think there's a candidate exoplanet around this star because we saw a dip in light. But TESS is, the imaging is such that one image could have 100 stars that are variable. The big deal thing is that which of those variable stars are actual variable stars. So anybody who knows about variable stars knows that there are all kinds of variable stars. Some stars just naturally pulsate and they become variable that way. Some stars are variable because there's two stars in a binary or three systems, but there's two stars and they rotate around each other. And as they rotate around each other, the light curve changes. You want to eliminate those from an exoplanet survey. So you find them by TESS or some satellite system saying, go look over here. And then we come in with our telescope and we say, yep, that's a real exoplanet star, or no, that is a typical variable star. So we get some help because I've thought about this too. What if I just randomly chose a star and started looking at it? Maybe I'll find an exoplanet, maybe I won't. You know, I have lots of time, but I don't have that much time, right? There's trillions of stars in the universe, right? Even in our own galaxy, right? So anyways, okay, moving on. I'm not gonna talk about this. This is fancy. Okay, so here's another light curve. This is actually, going to go back to your question about what happens to some of these planets, WASP-12. You don't want to live there. But this is the light curve from WASP-12, and I'll show you a picture of WASP-12 in a bit. But this is what we get. So here, back to your question again about variability. These lines here, these are all the comparison stars. And notice one thing, look at these comparison stars, look at the data point. I know there's a little bit of noise here, but look at it. I mean, I could kind of draw a line through there. Why is there this variability? Remember what I said, that the path of a photon has to go through all kinds of crazy stuff, including the atmosphere? This variability, this noise, that we're measuring. So each one of these is a picture. Yes, go ahead.
What's the time period on that chart?
This one, okay, I'm going to explain that in a minute. No, it's okay. Each one of these points is a individual image that we took of some stars, and we use our differential photometry to measure the energy or flux, as it's called, that comes from that star. And so you look at these stars, these comparison stars, you can see that they're pretty flat for the most part. We're able to then say, here's our transiting exoplanet. Here it is, the planet is not in front of the star. It starts to move in front of the star, starting here. And then it slowly moves across the face of the star and it comes back out the other side. So that's what we're looking at. I'm gonna not talk about this stuff right now. It's not, that's not due. Back to your time question. I don't know how best to explain this, but one of the valuable things of little ground-based observatories like my observatory or the observatory here is that we can help the scientists with these big fancy telescopes that are very expensive to operate. It's hard. Scientists fight to get time on one of those fancy telescopes. They fight for it. And they might, if they're lucky, they might get a couple of hours. Some of these transits, as I said, are 6 hours long. How many James Webb Space Telescope observation sessions get to last 6 hours? Probably very few, if any. So people like us, we can come in with our little telescope with plenty of time. We can lock onto a star for 6 or 7 hours and look at it. And so this time scale down here allows me to compare my observation with, I work with people all around the world. I work with a guy in Brazil, and he's looking at stars, I'm looking at stars. We can compare our data for a given transit by making sure that we have the same time scale. So to your question, this has got a weird unit. It's called barocentric Julian date. It's basically days, but if you want to, you can convert that to hours. So this light curve is probably, if I recall, WASP 12 is probably about, this duration here is about 2 hours our time, maybe 2.5 hours, right? Okay, so this is a light curve. I'm not going to talk a lot about this, but again, in exoplanet research, one of the things that you're trying to do is, again, you're sharing data with lots of different people, right? So you want to have the same language. And so this is just one way of our developing the same language. If I go back to that light curve, here is the light coming from the host star, and the planet is not in front of it. The planet starts to move in front of the star, and so the light starts to dip. Why is there a little line? Because the planet has this, even though it's tiny, it still has a finite width, right? It takes a few minutes for that planet to just touch this edge of the star, and then it takes a few, it takes a little bit of time for the whole thing to be covering the star. That's what we're looking at right here. And so to kind of have the same common language, we call this so-called ingress, where it just touches the star. We call that the T1 point. As it comes out on the other side, the same thing is happening, but now it's covering the whole star, and now parts of it move off of the star until finally it's no longer touching the star. We call that the T4 point. Those are just common language, so that by having a common time scale, that's why we use this weird time scale. By having a common time scale, I can talk to my Brazilian friend and we can compare exact moments in time. Forget the time zones, forget all kinds of different things that can happen. But we can compare events that happen 1,000 light years away down to the second. Yeah.
So how many times do you have to get a transit before you can say, or we have a
Exoplanet?
exoplanet as opposed to like a comet or something like that?
That's an excellent question. Okay, so how many times do we have to, let's take that in a couple pieces, because the common piece is a separate question. How many times do I have to look at a transit before I could say, yeah, that's an exoplanet that's not a variable star? It's kind of a statistical thing, but the typical rule of thumb is that we have to observe these transits. Somebody has to observe these transits at least 3 or 4 times before we're certain that, you know, we're looking at an actual exoplanet transit. The other way, and I'm not going to go into it here, the other way that we know it's a planet, not a star, is that if I have a binary star that's crossing in front of it, the curve is going to look very different. It's much more of a V shape, because the relative size of most binary systems, the relative size of the stars that are going around, they're closer to each other, right? So it's going to be a deeper curve, and it's also going to have a different shape. But your question is a good one. How many times do we have to look at it? 3 or 4 times. That's why there's some of these groups that I'm a part of with my little ground-based telescope. The scientists will say, hey, would you go please look at this star for us? Because we've looked at it a couple times. We need to look at it more often. And because we need to build up a good statistical database that says, yep, it's a confirmed planet, or no, there's something funky going on. The other thing that, and it's not part of this, but it kind of relates to your question, is if we look at it multiple times, sometimes we see little, and you'll see this in my data, you'll see little variations. That could mean that there's another planet in the vicinity that's changing. So here's the thing. Planets generally affect each other. If their parent star affects, you know, they all have a gravitational pull, as she said, right? So if there's some unseen planet, it's going to perturb, as it's called, some planet that I'm looking at, and that would show up in the light curve, and that could show up in differences. So again, we want to collect enough data to be able to say, yep, that's a confirmed planet, and it's probably by itself, or it's not affected. But
have you ever seen one? Like we just had, last month we had the planetary alignment. Do you ever get ones where you have such a perturbation where you think there's multiple planets around that same star?
I can't vouch for that in my data, but I bet it's there someplace. I've not seen it. So I've only collected a couple hundred of these light curves, so I'm just a newbie. There's still a lot to learn. Okay. Okay. So that was the only point here I wanted to make, is that to have a common language, because there's so many of us doing this thing. I think one group that I'm part of, there's like 1,000 people involved in it. That sounds crazy, right? But think about getting 1,000 people to try to all talk in the same common language, so that when you share this data, you can start drawing some conclusions. You know, you're back to your question again. I can collect one light curve, but I can collect 2, but it's maybe even better for you to collect one, and you to collect one, and me to collect one. So now we can pool our data together, and some crazy stuff that's going on with my system maybe is not the same as your stuff. And from that, we can figure out what's going on. You know, what kind of a planet are we looking at? Is it a real planet? That's what happens. So this is the common language thing. So I'll move on. I'm not going to talk about this. This is another parameter. Okay, so one really important thing, she mentioned life. If you lived on, let's say it's not even a hot Jupiter, but if you lived on Jupiter, how much would you weigh? Do you know how much you weigh if you lived on Jupiter? I'm not going to insult you, but I'm going to tell you it's not what you weigh now. Right? What would you weigh? What do you think? Yeah.
Oh, I think you get that.
Oh, okay. Anybody. I'll choose anybody. Never ask a woman about her weight.
1,000 kilograms.
Probably, possibly, right? You'd weigh a heck of a lot more. Because the more massive a planet, the more its gravitational pull. So why do you see those pictures of the astronauts on the moon hopping up, 6 feet in the air, or just, because the moon is so small, the gravitational pull is so small. But if you were on Jupiter, you would weigh hundreds. I'm already overweight. I would be really overweight on Jupiter. I mean, I probably weigh close to a ton on Jupiter, right?
Some planets don't have gravity.
All planets have gravity.
Oh, they do?
Anything that's got mass has gravity. The smaller it is, the less gravity. The larger it is, the more gravity. So why do we care? So what I'm trying to get at is, why do we care about the size of the planet? Because she asked the question, or she said, NASA's really interested in, is there life on this planet? The life that I'm going to find on a planet like a Jupiter, even if I could breathe the weird atmosphere, the methanes or whatever, it would be very different from what it is here, right? 1,000-pound guy like me would be a flat little pancake on Jupiter. It's going to be a very different kind of life. So if we're looking for life like we find on Earth, we want to find Earth-sized planets, and that's the whole point of this, of why we do, why we care about the planet radius. Basically, what's the size of the planet? Because we want to find planets that are kind of like Earth. So that's why we're doing this.
What's the closest exoplanet?
What's that?
What's the closest exoplanet?
That I've looked at, or just that's around? So Proxima Centauri. Does anybody? Have you ever heard of that? Alpha Centauri, right? What's the distinction of the Centauri system?
It's a triple star system. Proxima is the closest to
Closest to Earth, about 4 light years away. That's the closest star. Turns out, we're pretty sure that the Proxima Centauri system has exoplanets around it. So that's a good question. Now, do they? Barnard Star's, yeah, Barnard Star's another one that's close. What's the distance?
about 6.6 light years.
Yeah, so it's a little farther away, but so astronomers call that the local neighborhood, right? Well, if we're, even though it's trillions of miles to a light year, it's the local neighborhood. So Proxima Centauri is in a local neighborhood. Barnard Star, I think out to Sirius, which is about 10 light years away. That's all kind of local neighborhood. So the closest exoplanets that we know of are about 4 light years away. So.
Not very close.
Not very close. You know, and that's why, despite all of our efforts to try to find life on these planets, you know, we don't hear anything from Proxima Centauri. You've been, there's Jay. Your radio telescopes, have you picked up any SETI?
No.
Nope. Never picked up any extraterrestrials, right? Yeah, but we're still looking, so. Okay, so those are good questions. Man, I didn't know the audience here, so there's some really heavy-duty science here. But basically, if we know the size of the planet relative to the size of the star, that's what this slide is about. My observations will deliver data that tells me the size of the planet that I'm looking at. If I know the size of the star, and then I use the radial velocity method, I know the mass of the planet, now all of a sudden I could start saying, hey, it's a hot Jupiter. Oh no, it's a terrestrial. Maybe there's life there, right? So I can start to figure out what kind of planet am I dealing with. How do I know the size of the star? Well, it turns out that a long time ago, two guys, I can't remember the first names, Hertzsprung and Russell. You were shaking your head, you know, right? They figured out that there's a relationship between the brightness of a star and its surface temperature. Now, what's the surface of a star? It's the part that really emits the light. A star is gas, right? So it doesn't really have a surface, but there's a certain portion of it that emits the light. So that's what the temperature is. So our sun, does anybody know what the temperature of our sun is, roughly? Well, inside it's 100 million. That's true. What?
Surface or interior?
Surface. Yeah, about 5,000, 5,500, I think, or something like that. So it's actually, there it is right there. This says that it's just a little under 6,000. And by the way, this is a temperature scale. It's called kelvins, doesn't matter. You just think about it as pretty hot, right? Now, you're right. Inside the star where the fusion is going on, that's really hot. That's like hundreds of millions of degrees. But the surface that we look at is this. But it turns out there's a relationship between the temperature of a star, and it's a little backwards here. This is cooler stars, this is more hotter stars. The hotter a star is, the brighter it's going to be. And then you can also relate the radius of the star. So in order to determine the radius of the star, so I said it's really important for us to figure out our planet, what's our radius of our planet, and our data gives us the radius of our planet relative to the radius of the parent star. We can figure out what the parent star radius is by going to this diagram. All we have to do is look at it, and scientists do this all the time. They measure the temperature of stars all the time with spectroscopy, right? They measure, you guys have a spectrometer here on your telescope, right? So you could do this, yeah, on the 18-inch. You could, yeah, so you can use methods to determine what the temperature of a star is, and from that, and also kind of the class of the star, you can figure out kind of how big the star is. And now you've got your other part of the equation, and now you know, am I looking at a big gas giant or am I looking at a little Earth? And she wants to find the Earths because that's where there'll be life. And she'll find a boyfriend. I made that up, sorry. Okay. Okay, so what are we, I'm not going to spend a lot of time on this. This is just a light curve again. What are we trying to do? And when I do an observation, what am I looking for? I'm looking for this ingress and egress time because I want to know when something is happening. I'm looking at this T1, T4, so these are related. I'm looking at a transit midpoint time. I'm looking at how deep this light curve is. And again, remember, this looks like it's a deep curve, but it's really, really, really faint. You would never, ever be able to detect the change with your eye. The only way we can detect these changes is using really sophisticated software. So, and there's our comparison curves. We have some other things that we look at, but a really big one, I said I share data with people around the world and with other scientists. One of the first questions they ask is, how good is your data? And if I can prove that I got good data, it's acceptable and maybe somebody will use it. If my data's trash, they throw it out the window. That's just a natural thing, right? We don't want garbage, yeah?
I was going to add something about that. It's difficult to understand how hard it is to do this stuff. A very good astronomer, Peter Van de Kamp, back in the 50s and 60s, thought he had seen this kind of stuff on Barnard's stuff.
Right.
He was, his stuff was very believable, it was very good, but it all turned out to be something in his telescope system.
Right.
That was generating that, and then it became a laughing stock because it pursued that.
That's a painful but true story. Yeah. So what you described, I call it systematics. So things that are in my telescope, I have to rule those out. Because, I mean, I don't embarrass easily, but I don't want to send some good scientists junky data, waste their time. And so, so that's a big deal thing. But we'll move along. And okay, so here's a Nubia Blanca Observatory. This is my observatory. There's the chief investigator right there, Aero.
What's his name?
Aero, A-E-R-O. Now this is, you guys have seen the dome here. This is my little dome. It's only 10 foot, but inside of it, I have this really nice fancy telescope. This is what I use. So here's the telescope. It's a 0.4 meter telescope, so that's pretty good size. It's not as big as the 18-inch, it's just a little under it, but that's pretty good size. Pretty hefty mount. It's really important when you're looking at a particular star for 6 hours at a time that you track it really well. That's a really important deal. And there are ways to do that, but one of the ways to do that is to have a good mounting system. Here's the very fancy, I call it very fancy camera that I use. So we're taking pictures to create light curves. I'm going to show you that. Here's a picture. We're taking pictures to create a light curve. Now, where's the light curve in this thing? Turns out, actually, there's my star right there. I happen to know it. This is, actually, I don't remember what star this is, but I do know, I do happen to know that that's the target star that we're looking at. What is that? It's just a blob of light, right? But I collect 300 of these things, and I use some special software, and I can create that light curve that I can then, if it's good quality, share with somebody who then compares it to their light curve, and they say, yeah, we got an exoplanet, or no, we've got junk.
Does it for a light curve to happen, does it need like a certain habitat, or could it just like form?
Yeah. So her question is just back to what she asked earlier. Can we correlate light curves to life on a planet or to some possibility of life? Yes and no. Not so much directly. No, there's really, you know, the thing that she said about Earth-like planets, the size of Earth, let's say, those are hard to see. So yeah, in that sense, the light curve would be a little tiny dip. But it's not directly correlated. The light curve is just a technique for us to be able to figure out what we're looking at. In terms of, if I lived on this exoplanet and I was a bug on that exoplanet or whatever, I wouldn't care what the light curve looked like for my planet. I'm just living there. So, but here I am 1,000 light years away from that planet, and that's how I figure out that there's something, you know, there's an object there. I can't tell what's on that planet. I don't know anything about it other than maybe it's big, maybe it's little, maybe it's hot, maybe it's cold, but that's all I can tell, you know. And as Jay said, we have yet to detect extraterrestrial life on any of these things from radio signals or whatever it is, right? Okay, so I'm going to show you a few light curves, and I'm going to move through these quickly. So here's a planet called Kelt 3b. They have really weird names. You know what Kelt stands for? It stands for Kilodegree Extremely Little Telescope. So these scientists have a sense of humor, right? So it turns out that this kind of goes back to your question, how do we find exoplanets? Some people created this Kelt system, and they took a bunch of pictures of the sky, big pictures, and then somebody went and took one of those pictures and said, okay, there's 1,000 stars in here. I'm going to start poking my way through them, and I'm going to see if I can find a star with an exoplanet around it. One of them they found was Kelt 3b. It's a gas giant. By the way, this comes from a NASA site. Beautiful site. If you ever want to go out there, just Google NASA exoplanet catalog. You can go grab this stuff and look at it on your own if you're interested. It's really, I think it's a cool site. The planet is about 1.5, 2 times, maybe 1.5 times the size of Jupiter. And so that's what this picture is down here. Here's the Earth, and here's this Kelt 3b. This is what it looks like. It was discovered by the transit method. It weighs almost 2 times Jupiter. So if I look at this number and this number, I would say that I'd weigh even more on this planet than I weigh on Jupiter, because the density of the mass of this planet, again, I said, remember, your weight is going to be related to the mass of the object you're standing on. And so you're going to be pretty heavy here. It was discovered almost 12 years ago. It's really, really close to its host star. So what is an astronomical unit? The Earth is 1 astronomical unit away from our sun. Does anybody know what an astronomical unit in miles is? 93 million miles, right? This planet is 4/100ths of that. So what would that make it, math heads? Do a quick multiplication. 0.04 times 93 million is what?
4,000 miles.
About 4,000 miles. I mean, you might say, well, that's a long distance, but not if you're next to a hot star. And look at well, you don't know this necessarily, but if you do know anything about stars in the standard, you seem to know it. What's an F-type star? Where's that put it into the?
It puts it a step below our sun, but it's still.
Step above, actually, hotter.
Oh, sorry.
Yeah. This is a bigger, hotter star than our sun. And we've got a planet that's 4,000 miles away from it. It's blazing hot on that. 4 million, that's right, 4 million. And so that's what this picture shows. So here's the orbit of Mercury, which we know is a really hot planet. This is all relative. Here's the orbit of Mercury superimposed on the orbit. Here's the parent star, host star. Here's the orbit of Kelt 3b. Really, really close, right? Here's a light curve I collected from Kelt 3b. I think it's interesting, but you know, I'm not going to spend time talking about it. Other than to tell George that here's some of the systematics that we look at to estimate the quality of our data. But I'm not going to go into explaining what that means, but I can if you want. But go ahead.
How do they stop Jupiter retaining their gas? It was in you at that kind of heat that the gas would be gone. I don't understand that.
That is a really good question that I was just talking about with her, and I don't know. You would think that you're so close to a star, the solar wind from that star has got to be just, and what kind of gas are we talking about? Mostly probably helium and hydrogen, right? That's what Jupiter is. So that's really light stuff. That's hot. in the blowing wind, I mean, it moves my landscaping material around here all the time. You can imagine what it does to a star.
Sure, it sounds like a presentation for you.
Yeah. But, so,
I'm sure everybody knows, man.
no, that's a good question, and I don't know the answer to it. But here's another one. Now we're going to get to the bad boy. WASP 12B. It's this one in particular. Look at this. This star is almost 1,400 light years away. It's far away. It is so close to its parent star that its parent star is tugging on it, because kind of your question is tugging on it, making it egg-shaped. Look how NASA describes it. The doomed planet, WASP-B, is a hot Jupiter. It's getting ripped apart, basically. And here's an interesting thing. Here's a question that I asked myself. Okay, so it's 1,400 light years away. If I observe a transit for this planet today, I'm actually looking at something that happened 1,400 years ago, right? So what's 1,400? AD 1000. What was going on here in AD 1000? That's weird. Is that planet still there? I don't know.
Probably not.
Maybe not. But it's getting ripped apart because it's so close to its sun. Not only are we not worried about its atmosphere, we're worried about the whole planet. Yeah. So, okay. So here's a light curve of WASP 12B. Looks like a normal light curve. Back to your question. Look at this light curve from Kelt 3, which is close, but not being ripped apart. Compared to this one, they look the same to me. So it's hard to tell from a light curve what's actually going on the planet. You have to know a little bit more about it. But that was a very good question that you had. Okay, here's another one. All these I've observed in my observatory, right? And these pictures I didn't get from my observatory, but these are pictures I got from NASA for these planets that we looked at. Here's a planet it's another hot Jupiter. By the way, that's the best that I can do in my observatory. Corinne was saying, hey, can we take a look at some terrestrials? Well, not really, not from my little telescope, because it's too small. There's too much atmosphere, there's too much turbulence. The light curve is such a tiny little dip. You really need, like you said, you need the James Webb Space Telescope to see that. But let's see, what can we say about this planet? So here we go again. It's another huge planet. Here's the Earth, there's the planet, huge. It's bigger than Jupiter. You weigh a lot there. Look at, it's almost 3.5 masses bigger. So if you weighed 1,000 pounds, let's say, on Jupiter, you'd weigh 3,500 pounds on this planet. Flatter pancake than you would be on Jupiter. I would be. This is just the relative distances from a star. Now, one thing about this picture that's kind of cool, see this, it's kind of hard to see, but you see this kind of grayish area in here? Yeah, they call that the habitable zone, what she was calling the Goldilocks zone. This is where, if there was a planet in this system that could potentially have life like we know it on Earth, it would be someplace in here. So again, we're looking at this hot Jupiter, which is really close, but maybe someday, through better techniques or better telescopes, we'll discover a few planets in here, and maybe there is something in here that's a terrestrial. We don't know. So that's the habitable zone. There's the light curve, now a little deeper light curve. And then I think maybe I have one or two more. Here's another gas giant that I've looked at, HAT P13b. Again, weird names. I forgot what HAT stands for. Something, I don't know. Another gas giant, very close. Okay, light curve, a little different. Again, one of the differences, and I'm not spending a lot of time on this because it gets boring very quickly, except to geeks like me and Corinne. There's just interesting stuff going on here with these light curves. And one of the things that I'm amazed by, and I think somebody said earlier, wow, we're actually seeing this stuff. I'm just this guy with a telescope out in Berthoud, and I'm doing stuff that in the 50s would have just been
It was science fiction.
science fiction.
I was an astronomy major in the 60s. this stuff is so far beyond.
Yeah, because it changes stuff. But still the cool thing, as I said at the beginning, the really cool thing is that folks like us can contribute to the science with the kind of tools that we have now and we had. So that's kind of fun. Here's another, okay, last one, KPS-1b, another big boy. It's almost 900 light years away from Earth. So when I'm looking at these transits, like this transit of KPS-1b, I'm looking at something that I looked at this in last February, our time. I'm looking at an event that occurred 900 years ago. Because it took light from that event 900 years to travel from the star to my little telescope. When I think about that, that's an amazing thing.
Your telescope is a time machine.
It is a time machine. Yeah. So, okay, the last thing I just want to show you all, NASA has some really good stuff. This is one of them that I really like. If you're interested in exoplanets, you want to learn a little bit more, do you want to dabble in it, go to the site. One of the really cool things is, for all of you, is that NASA has a really good what's called citizen science program. You can actually, you don't have to have a telescope even. You can go and join their citizen science program, and especially educators, they really are targeting educators. You can join their program and they'll provide data that they collected that you can analyze. So now you're participating in the creation of the science. Yeah, it's cool, yeah.
That's similar to Zooniverse, right?
Yes, there are various programs like that, but for exoplanets, NASA has a Citizen ExoWatch program, and you don't have to have a telescope. If you have a telescope, that's great. They'll take your data if it's good quality, but you can basically become a citizen scientist. And I participate in some of those meetings, and a lot of the folks on these calls are educators who are leading STEM programs, and they don't have access to telescopes, but they have access to data. And why is it important? Because again, these scientists don't have as much time as a retired guy like me or people like y'all. I'm not going to assume you have time, but you probably have more time than some scientists who's worried about writing a paper and getting, a grant and all that. There's plenty of opportunities to contribute. This is a good place to start. The Exoplanet catalog is a good one to start. So, you want to? All right. Well, you do because you're being recorded.
Okay, I promise we're almost done.
That's it.
Our data that we collected over the summer went to two different groups, mainly. The AAVSO, which is the American Associate of Variable Star Observers, and the TFOP, which is the Test Follow-Up Observation Program. So both of these are in coordination with MIT and NASA, and we are able to work with astronomers from around the globe, like he said, and we collect data, we look at other people, we check other people's work, we do all this stuff, and it helps NASA sort through the 24/7 images that they're receiving from these satellites that are staring up into the sky all the time. Yeah, so we'd like to thank Ms. Hansen, Ms. Domenico, and the STEM program. Yes, well, and then Dennis.
I want to recognize, they're not here, Dennis Conti is a lead on the AAVSO group. She mentioned the AAVSO group. He's one of the experts that I work with. And Dr. Karen Collins out of the Harvard Smithsonian Center for Astrophysics. I am kind of a scientist, but she allows little schmucks like me to play in her sandbox. And so I'm grateful to both of those folks for the things that I've learned and for the opportunity to contribute to the science. It's a great thing. And I'm looking forward to more of you all contributing to the science too. So I think that's it. Are we done?
Yeah.
Any other questions?
Sorry it took us so long to get through this, but you can hopefully tell that we're excited.
Considering the weather is not cooperating at all.
Well, we didn't drag it out. We tried to cut it off. But anyways, thank you for your attention. These are really good questions, by the way. I really am impressed by the questions that I heard from you all. They're really good questions. So
If you don't feel comfortable asking in front of the group, we'll be around after to individual. Thank you.